Now that we've seen some situations we can model with first-order linear equations, let's look at some nonlinear situations. So one that is sort of common is modeling population growth. Now we have seen a linear model of population growth right here, where your population growth is just, the rate of population growth is just proportional to the size of the population. So let's suppose we have a population that would grow like that if there were no constraints on its growth, but there's actually some sort of maximum population that the environment can support, capital K. This quantity is usually called the carrying capacity of the environment. So to incorporate this maximum population into our model, we're going to have to modify this differential equation. But one key thing that we want to accomplish with the modification that we make is that when our population is near zero, that is far from the carrying capacity, the differential equation, whatever modification we make to the differential equation, should make it look like the original differential equation, dp dt equals your growth rate times p. Because if we're far from the carrying capacity, then it's as if there's not really anything limiting the growth of the population yet. And so the population growth should look like our original differential equation. So with this in mind, let's see what we can do. So since there's nothing about the situation that explicitly mentions time affecting the growth rate of the population, we can expect that whatever equation we write down is going to be autonomous. So however we change this right-hand side, t won't show up. And we've seen that one nice way to think about autonomous equations is to think about them in terms of their equilibrium solutions. So let's draw a phase portrait for what we would expect for solutions on the p-axis. Remember, we can only draw a phase line when the equation is autonomous, so that's why we need to make sure it's an autonomous situation first. So we know there is an equilibrium at zero because if there are no individuals in the population, there's going to stay no individuals in the population. That's sort of how populations work. And for negative values of p, we don't really care what happens to the phase line because negative populations don't really make sense. So we don't really care what happens down here. Now, I'm not saying that the differential equation won't be defined for negative p-values. I'm just saying we won't care if these solutions increase or decrease just because they physically are never going to happen anyway. So we have this one equilibrium solution at zero. But also, we have another equilibrium solution at the carrying capacity, because if we have exactly the population allowed by the carrying capacity, any more population, we'd be exceeding the carrying capacity of the environment, and so the population should dwindle a little bit because there are just too many of them. And so that means, in addition to having this equilibrium, if we're above the carrying capacity, the population should decrease. If we're below the carrying capacity, that means there's room for more population, and so natural population growth should take over, and the population should increase. So we get this kind of phase portrait. An equilibrium solution at zero, which probably will end up being unstable, but we don't actually care about the negative p-values. And then this equilibrium at k, that is a stable equilibrium. So with two equilibria, that gives us a good start on how we should modify this differential equation. So probably we should stick with the r times p that we started with. We just need another factor here that produces the equilibrium at k. And sort of a first guess for what would work well is p minus k, because this would produce an equilibrium solution at k. But there are two issues with this. So first issue is if we draw a phase line for this differential equation, right, we do get the equilibrium at 0, we do get an equilibrium at k, but the directions that the solutions go are all backwards. So this one goes that way, this one goes that way, this one goes that way, and that's backwards. So we need a minus sign in front of our differential equation. So that will fix the first problem. So we're going to have dp dt equals minus r times p minus k. But actually, there's another problem with this differential equation or this modification that we've made to the differential equation, and that is, remember that when p is close to 0, we want our differential equation to look approximately like just r times p. So let's see what happens to our differential equation when p is near 0. So when p is near 0, we can't just plug in 0 for this factor of p, because that's the factor that makes 0 an equilibrium, so we need to keep that. But if p is near 0, then this second factor, the p minus k factor, is approximately 0 minus k. So when p is near 0, our differential equation turns into dp dt equals negative r times p times minus k. So this would give us k times r times p. And that's just not what we wanted. So although this modification we've made to the differential equation is a good start, it gets the equilibria that we want, but it doesn't capture this behavior that when p is near 0, we ought to be growing as if we have unconstrained population growth. So what we need to do is, right, it would have been nice if this factor right here was approximately -1, right? If this had come out to be approximately -1 when p is near 0, then this k wouldn't be here. We'd have a 1 here instead. And that would be what we want. So what we need to do is change this factor, this p minus k factor, so that this is approximately -1 when p is small, near 0. And there's sort of a nice trick to make that happen. And the trick is, so minus r times p, rather than just doing p minus k, we can do p over k minus 1. You see, this still has the effect of producing an equilibrium at k. If we plug in k for p, then this factor goes to 0. So we do get the equilibrium we want. Also, the phase portrait comes out how we want as well. But now when we make our approximation where p is near 0, the differential equation turns into, so minus r times p times, so if p is near 0, then p over k is approximately 0, minus 1, so we get rp. And that's what we wanted. So if our population is near 0, then we get the population growth as if it's unconstrained. So this is the modification to the differential equation that we'll use when we have constrained population growth, when there's some sort of maximum carrying capacity. This isn't the only way to modify the original model for population growth, but it's a very common way. This is called logistic growth. Okay, so now that we have this differential equation, let's solve it and see what we get. It is an autonomous equation, so we should be able to solve this treating it as a separable equation, because every autonomous equation is separable. So let's go ahead and separate our variables. So dp over, so I'm going to divide by p times this factor here. So I get p times p over k minus 1 equals minus r dt. And let's see, next we need to integrate on both sides. But on the left-hand side, to integrate here, we're going to have to do partial fractions. So let's do that now. So we have 1 over p times p over k minus 1 should be equal to some number over p plus some other number over p over k minus 1, right? So now we can clear denominators, multiply both sides by p times p over k minus 1. We get 1 equals capital A times p over k minus 1 plus capital B times p. Now we can plug in p equals 0 into this. Right? This equation is supposed to be true for every value of p. So in particular, it's true for p equals 0. So when we do that, we get 1 equals minus a. So a is minus 1. And when we plug in k, we get 1 equals, now plugging in k for p makes this first part in parentheses 0, so the a part goes away, and we're just left with b, so we get k times b, and that means that b is 1 over k. All right, so now that we have our coefficients for partial fractions, we can continue solving. So on the left-hand side, we have a, which is minus 1 over p, plus b, which is 1 over k, times 1 over p over k minus 1, equals minus r dt. Okay, and I'm missing a dp on the right-hand side. All right. One last thing before we integrate, we might as well, I guess, distribute this k through here. That looks like it's just going to make things a little nicer. So minus 1 over p plus 1 over p minus k all times dp equals minus r dt. All right, now we can integrate finally. So integrate on both sides. The left-hand integral is going to be the hard one. So integral of minus 1 over p, that's minus natural log of p. Population has to be positive, so I'm going to not bother writing an absolute value here. Plus natural log of p minus k equals, then on the right-hand side, minus r times t plus a constant. Don't forget about your constant of integration. Now, we need to solve this for p, so we're going to have to get these two occurrences of p, here and here, together somehow. Since they're in separate logs, we'd better at least put them in the same logarithm. So we get natural log of p minus k over p equals, on the right-hand side, minus rt plus some constant. Now we can exponentiate. So on the left-hand side, p minus k over p. And on the right-hand side, e to the minus rt plus c. As usual, we can write this as e to the c times e to the minus rt, and then rename e to the c capital A. So capital A e to the minus rt. All right, let's see. Next, I guess we can do this division. So we get 1 minus k over p equals AE to the minus RT. And now, right, P only shows up once in this equation now, so we can just solve this for P. So move the 1 over minus K over P equals AE to the minus RT minus 1, multiply by minus 1, K over P equals 1 minus AE to the minus RT. A is an arbitrary constant, so I guess we could absorb this minus sign into A and make this a plus if we wanted to. I might do that later. Next, we need to take reciprocals. So then we get P over K equals 1 over 1 minus AE to the minus RT. And then finally, multiply by K. So we get our population function is K over 1 minus AE to the minus RT. Okay, so remember R is our natural growth rate. K is our carrying capacity. And A is an arbitrary constant that will be determined by whatever initial condition we happen to have. So we were able to solve this differential equation for an explicit solution. So next we should probably investigate what these solutions look like, just to see what this sort of population model actually gives us for solutions.